Hello and welcome to this video on the graphing of linear functions. Now this is linear functions of a single independent variable that we're graphing here. Examples I'm taking are taken straight out of an intermediate algebra text just to give you the context of these problems. All right. What type of, what depth I'm going into here. All right, so I just have a few examples for you. Let's begin. Alright, so before I get to my examples, what we're doing here is I'm going to be graphing linear functions of a single independent variable of the form, well, of the following form. So linear functions. So we're going to be graphing functions of this form, f of x, or the value of function f at x equals m times x plus b, where m and b are real numbers. Okay, and when a function's in this form, and you might have seen this also as, remember, f of x could represent the output, right? X is the input, and then m times x plus b, or this f of x is the output. That could also be represented by y, right? Like y coordinates, outputs, y equals mx plus b. The m in this case, when it's in this form, the m is referred to as the slope of the line, which is just the ratio of, what in some books is called the rise to the run, rise divided by run, otherwise known as vertical change, the amount of distance I would move up and down, divided by the horizontal change, the run, the amount of distance I would move left and right to get from one point of the line to another point on the line. Now when we're talking rise and run, if rise is a positive number, that means I'm moving up. If rise is a negative number, means I'm moving down. Alright, and then for the run, if the run is a positive number, means I'm moving to the right, increasing the values of x, and if the run is a negative number, less than 0, it means I'm moving to the left. Okay, just keep that in mind when I talk about rise and run and moving so many units in certain directions. And the b there is the y coordinate of the y-intercept. Right, the point of the graph that's on the y-axis, which means it has an x-coordinate of 0, and hopefully you can see that if I replace the x-coordinate with 0, x with 0, you'd have m times 0 plus b, giving you a y-coordinate of b. Right? 0 corresponds to b. The value of f at 0, or whatever the function is, this is f here, but whatever the function is, the value of this function at 0 is b. All right. And how we're going to graph them. All right. I'll write out steps for them when we actually get into my examples. All right, so I just want a brief introduction to what we're doing here, what we're looking at, and now I have some examples where I'm graphing some linear functions, all right, plotting points. All right, so the first of these, I have several, so graph each, more than just this one. Graph each linear function. So I have f of x, function f of x equals 2x minus 3, right? So the input is x, the output is 2 times that x minus 3. Now you could do what I've done in previous videos on graphing a function where you make a table of inputs and outputs and see what ordered pairs, what points need to be plotted, and then plot enough to where you see a pattern forming and then fill in the rest of that pattern, fill in the complete graph. You can do that. There's nothing wrong with that. But if you recognize that, hey, this is in that form I was talking about, the y equals mx plus b, where, m here is positive 2, right? The coefficient of x, that's the slope. And b is negative 3, right? That's plus negative 3 if you want to think of it that way. If you recognize that, hey, this is in that form, mx plus b, then you should know that it's a linear graph, right? Its graph is going to be a straight line. So in that case, you really only need 2 points, right? You only need 2 points to determine a line. All right, so here are the steps I'm going to follow. Here are what I'm going to do to graph this. First, plot a point on the line. Now, if it's in this form, the easiest point to plot is the y-intercept. All right, so I'm just going to say the first thing I'll do when graphing an equation of this form is plot the y-intercept. So that in here, that would be 0 for the x, right? If you're on the y-axis, the x-coordinate 0. And if x is 0, you get 2 times 0 minus 3 as the output. Again, that's this b, the negative 3. The b is the y-coordinate of the y-intercept. Alright, so let me plot that. Now over here on my axes, I'm going to have each square represent 1 unit. Right? So this is 1 unit in the x direction, and each square in the y-axis also I'm going to have represent 1 unit. So I have 0 for the x, negative 3 for the y. So 0 for the x, I'm in the middle there, and then negative 3 for the y. So that's this location right here on the y-axis. So there's the y-intercept. There's the point 0, negative 3, if you want to label it, be my guest. And then I'm going to use the slope to find another point. And you could plug in another value and then, find an ordered pair that way. But I'm going to use the slope to find other points. Alright, so what do I mean by this? So I mentioned a second ago, that the slope of this line is 2, which if you think of that as a fraction with a numerator and a denominator, that's positive 2 over positive 1. Right? 2 divided by 1 is 2. So this positive 2 would be the rise, and this positive 1 would be the run. Okay. So if the rise is positive 2, that simply means I'm going to go up 2 units. And the run is positive 1. I mentioned on the previous page, right? If a run is positive, I'm going to go to the right 1 unit. Alright, and that's from a point that's already on the line. So don't start at the origin. Alright, notice that the origin, 0, 0, this is not on the line. I am not starting here. I am starting here. And I'll make that little note. Don't start at the origin automatically. Unless the origin is on the line, right? I'll put that in parentheses. Unless the origin is on the line. Right? You start at a point that's on the line. So the only point I know right now is this point right here, the y-intercept, 0, negative 3. So from this point, from 0, negative 3, I go, rise 2. Right? So I go up 2 units to negative 1 on the y-axis, and then run 1. So from here, from the point on the line, I go up 2, right 1, landing me at this location. All right. So here's another ordered pair, and again, I'll start labeling these. We've got here's 0, negative 3 that we already plotted, and then this point up here is 1 for the x, negative 1 for the y. And just to double check, let's see if that's a true ordered pair in this function. If x were 1, would the value of f at 1, would f of 1 be negative 1? Let's see. Replace x with 1. I'm just going to say it. 2 times 1 is 2. then minus 3 would indeed be negative 1. This point does belong to this function. And you could keep going. From this point, again, you have to start, don't just start at the origin, start from a point on the line. From this point, I use this slope to find another one. Use the rise up 2 and the run right 1, and now I'm here at this location, which has coordinates, right, that's positive 2 on the x, positive 1 on the y. All right, and again, just let's double check that. Is f of 2, is the value of the function when x is 2 equal to 1? Well, let's see, replace x with 2. 2 times 2 is 4. 4 minus 3 is indeed 1. So that ordered pair belongs to the function. Now, you don't have to go in this direction. Right? You could also think of the slope this way. Right? I said the slope was 2, right? M was 2. The coefficient of x in this mx plus b is 2. Now earlier I said you could think of 2 as 2 divided by 1 when you think of it as a fraction. Well, remember, a positive divided by a positive is positive, but so is a negative divided by a negative. You could also think of 2 as negative 2 divided by negative 1. Right? A negative divided by a negative is positive, so negative 2 divided by negative 1 is positive 2, and then use the rise and run here. So look at the numerator is the rise, how far up and down I go. All right, now the rise in this particular way I wrote the fraction is negative 2. A negative rise means I'm going down, so that's down 2 units. And then the run, the denominator, the horizontal movement, the run is negative 1. And you saw on the first page, when the run is negative, means I'm moving left, right? The values of x are decreasing, left 1 unit. So look at my picture again. Now I've got 3 ordered pairs that belong to this function, 3 solutions to this equation. I can plot some more. Again, start from one of the points and go down to left 1. So I see, look at you. Can you see it's working out? If I start from this point here, if I go down to left 1, I'm at this point. I go down 2, left 1, I'm at this point, the points I already have. And I can keep going. Down 2 units, so from negative 3 on the y-axis to negative 5, down 2 units, and then left 1, I'm at this location, which is the ordered pair negative 1, negative 5. And again, double check it. Let's see. When x is negative 1, is the output negative 5? Well, let's see. 2 times negative 1 is negative 2. Negative 2 minus 3 is indeed negative 5. That also works. And I could do this forever. Right? I could keep plotting points, go up 2, right 1, up 2, right 1, up 2, right 1, or go down 2, left 1, down 2, left 1, down 2, left 1, and keep plotting points forever. But, there are infinitely many of these ordered pairs, and there's no way you're going to possibly list them all, possibly draw them all. So we're going to fill in the rest of the graph, following this pattern. And I know based on the form, right, because I have a function that's in this mx plus b form, I know from experience now that the graph is going to be a straight line. Right? So a straight line going through these points here. Let's draw in the rest. I'm doing a ruler. You don't have to use a ruler, but right, so there's the graph of my function called f. All the solutions of this equation, all the ordered pairs that belong to this function. Okay, great. But that's how I'm going to plot all these equations that are in this, f of x equals mx plus b form. I'm going to plot the y-intercept, plot a point, and then use the slope to find other points. Use the rise and the run to move from one point on the line to another point on the line, and then finally, after I have a couple, I'll finish the graph by filling in the rest. All right, so here's another graph, another linear function. Now this is not called f. This is a function called g, capital G here. And the value of g at x, g of x, is negative 5 times x plus 4. So the input is x, and this over here is how do you calculate the output, right? The y-coordinates. All right, so first, like I said, the y-intercept. I'm going to plot a point, and the easiest point to find when you're in this form is the y-intercept, which would be, again, 0 for x always on the y-intercept when you're on the y-axis. And if x is 0, you have 4 for y. Right? So again, I'm going to have every square here on the axes represent 1 unit. So 0 on the x, and then 1, 2, 3, 4, positive 4 on the y. That's this location right here, and I will also label the point. There's 0, 4. All right. Okay, now for the use of the slope. All right, now this time the slope, right, the coefficient of the x is -5. Right, that lowercase m, the slope, is -5. All right, so you can think of this as a fraction in two ways. All right, this is a negative number. Now to get a negative number, I need to either take a negative number divided by a positive number, so that would be -5 divided by +1, that'll be -5, or I could also say this is equal to a positive number divided by a negative number. So +5 divided by -1. Both of these make -5. All right, so if I think of it this way, with the -5 divided by +1, my rise, right, the numerator, this is the how much do I go up and down. The rise is a negative number here, so that means I'm going down. I'd go down 5 units. And then the run, in this case, the denominator, right, which tells me how much I go left and right, is a positive number, right? The run is +1. So I'm going to go to the right 1 unit. So let's see what happens when I do that. So again, don't start from the origin, right? The origin is not on this graph. The origin is not the y-intercept. The y-intercept is up here. I start from this point. And then the slope is telling me to stay on the line. To get another point on the line, I go down 5 units and to the right 1 unit. So from 0, 4, I go down 1, 2, 3, 4, 5. So I went from a y coordinate of 4 down to a y coordinate of -1, and then right 1 unit. I'm at this location right here. All right, and that has coordinates of 1 for the x, -1 for the y. And again, double check. Does this ordered pair actually belong to the function g? When x is 1, would g of 1 would the value of the function be -1? Let's see. When x is 1, you'd have -5 times 1 is -5, plus 4 would be -1. That works. And then this is great. I mean, all you need to draw a line, since I know this is the form of a linear equation here, I can just draw a line once I have 2 points. All right. But I'm going to throw one more in, right, using this other interpretation of the slope, right? I thought of this as -5 divided by +1, or you could think of it as +5 divided by -1, right? Either way, it's -5. Now, if I think of the slope this way, the numerator, my rise, right, how much am I going up and down, is a +5, meaning I'm going up 5. But the denominator is negative, right? That's the run, how much I'm going, and that tells me I'm going left. Right? A negative run is, you go left 1. So I go up 5, left 1 from a point. So let's see, that works out, right? If I start from this point, I go up 5, left 1, I'm at the y-intercept again. And then from this point I go up 5 units. So from a y coordinate of 4 to a y coordinate of 9. And then left 1, I'm at this point right there. Right? This location. And this location is on the line and has coordinates of -1 for x, +9 for y. And double check, is that ordered pair, does that actually belong to this function g? When x is -1, would the output be 9? Well, let's see. -5 times -1 would be +5, plus 4 would be +9. So yes, that actually belongs. And you could do this forever. You could do this all day long. Keep going down 5, right 1, down 5, right 1, or up 5, left 1, up 5, left 1, and keep plotting points, and they're all going to fall on this same line, right? So now that I have at least 2 points, let's draw that line in. All right, so I got 2. So there we go, connect it all. Nice straight line here. It might have been a little off because of my ruler movement, but there we go. And there's a graph of this function called, capital G. Wonderful. But again, very simple. Just plot a point, and again, the easiest one's the y-intercept. Just plot a point on the graph, plot an ordered pair that belongs to the function, and then use that rise and run, use that slope to determine which way it's going. And you may have also noticed that, this line had a negative slope, right, -5, and you see what it looks like? As I move to the right, it's going down. It's pushing downward. Whereas when a line has a positive slope, right, like this line here, we had a slope of +2 in my first example. As I move to the right, the graph, goes up. So graph goes up to the right when I have a positive slope, and the graph goes down to the right when I have a negative slope. All right, hopefully you've noticed that. All right, great. All right, so here's another example where I have another, again, linear function of that form, mx plus b. Right? This time it's function h of x equals 3/2 times x plus 1. All right, and again, my units here are all going to be 1 unit long. All right, so 1 unit between each square going up and down. All right, so first I'm going to plot an easy point. All right, plot a point on the graph, the y-intercept. So that's 0 for the x-coordinate, and if the x-coordinate were 0, this would be nothing, and then you'd have 0 plus 1. You'd have 1 for the y-coordinate. Right? So let me plot that point. All right, so again, 0 for the x, +1 for the y, and that's this location here on the y-axis. Right. And I'll label the point. So there's the point 0, 1 right there. All right. And then from this point, right, not from the origin, from a point that's actually on the line, I'm going to use the slope. Now, being in this mx plus b form, we can tell what the slope is, what that m is, and I'm seeing that the m here, the slope of this line, is +3/2, right, the coefficient of x. Right, that's the m. And it's already written as a fraction. Right? I have a numerator and I have a denominator, so I can say what a rise and run are right now. The numerator is a +3, so the rise, I'm going to go up 3 units, right? A positive rise, I go up. And the run, the denominator, is a +2, so I'm going to go right 2 units. All right. Now again, you don't have to think of it this way. All right? This is a positive number, right? +3/2. Well, another way to get a positive number is to divide two negative numbers. So +3 divided by +2, is the same value as -3 divided by -2. Right? These are both +1.5, both +3/2. So you could also take go from a point on the line and go, rise down 3, right? Numerator's -3 here, and run -2, which is left 2. All right, so let's see if both directions give me points on the same line. All right, so I'm starting from the y-intercept, right, the point 0, 1, and let's do it with this first interpretation where I have +3/2, +3 divided by +2, up 3, right 2. So from this point, go up 3 units to a y-coordinate of 4, and then to the right 2 units. All right, so up 3 units, right 2 units. I'm at this location right there where that little dot is. I'm going to make it bigger. All right, and what are the coordinates of that point? Let's see. That has an x-coordinate of +2 and a y-coordinate of +4. Wonderful. And let's see. Let's actually check it. Is that ordered pair, does that actually belong to function h? When x is 2 is the output 4. So when I plug in 2 for x, now if I plug in 2 for x, can you see how the 2's would cancel? You'd have 2 in the numerator, 2 in the denominator, you'd be left with 3. And this would be 3 plus 1 or 4, exactly what the output is in my ordered pair here. Great. And I could keep going, go up 3, go up 3, right 2, and then I'm at this location. All right. Let's see where what that coordinate is. That'd be 4 for the x, and 5, 6, 7 for the y. All right, so this is the location 4, comma 7. Again, plug in 4 for x. 3 halves times 4 would be 6, and then plus 1 would be 7. Great. And again, you can keep doing that. Go up 3, right 2, up 3, right 2, and then keep plotting points all day long if you wanted. Or, again, if I look at it this way, negative 3 divided by negative 2 is the same as positive 3 divided by positive 2. They both end up being positive 3 halves. Go down 3, and then left 2. So you see down 3, left 2, down 3, left 2. And then from 0, 1, I go down 3, and then left 2. I'm at this location here. Alright, and I'll mark it off, make it a little bigger. This location right here, this point. And this point has coordinates, negative 2 for the x, negative 2 for the y. Again, let's see. Plug in negative 2 for x. 3 halves times negative 2 would be negative 6 halves, or negative 3 when you reduce it. And then plus 1 would be negative 2. It has that negative 2 as an output. Great. And again, you could keep going. Down 3, left 2. There's another point. Down 3, left 2. There's another point. All right, and I can plot points all day long with this method. But as I've said in the beginning, if you recognize, hey, this is mx plus b, this is a linear function, you only need 2 points. Right? So once you have at least 2 points, you can fill in the rest of the solutions, the rest of the ordered pairs that belong to this function. Let me line up the points here. Again, if you don't want to use a ruler, that's fine. And then and there you go, going that way forever, little arrows on the ends, and there we go. There is a graph of the function called h. I'll label that on my graph there. Great. And again, it's really that simple. Plot a point, and then use the slope. And notice again how this particular linear function had a positive slope, positive 3 halves, and you see how it goes up as you move to the right, up and to the right, just like the first example that had a positive slope. All right, and I have one last example here. So far we've seen a couple lines with a positive slope, one line with a negative slope. Well, what about a line with no slope, 0, a slope of 0, right? That's not positive or negative. So here's my last example in this video. I've got f of x equals 4. This is input x, and then the output is 4. Notice there's no x over here. If you wanted to write it in that mx plus b form, you could think of this as 0x, right? There's no x's over here, and then plus 4. You can think of it that way. But either way, it's input x, and no matter what you plug in for x, the output is 4. All right, so the first thing I'm going to plot, and the y-intercept, and just any point but the easiest in this form is the y-intercept. So when x is 0, what's the y? I said it a second ago. When x is 0, well, no matter what x is, y is 4. So the point 0, 4, I'm going to plot that. So 0 for x, and then 1, 2, 3, 4 for the y, and that's this location here on the y-axis. All right. Now, as I mentioned, right, there's no x in this expression over here. This is just the number 4, which you can think of as having 0x. So the m here, the slope, is 0, right? The coefficient of x. All right, now 0, you can put any denominator underneath it that's not 0, and it'll still be 0, right? So you can think of this as a fraction as 0 divided by 1. Or 0 divided by -1, or 0 divided by 2, or 0 divided by 10. It doesn't matter. If the numerator is 0 and the denominator is non-zero, then the result is 0. Right? So I have a rise of 0. Well, a rise of 0 would mean don't move up or down. Right? There is no movement up or down. And, again, I put a denominator of 1 here, right? Just so long as you put a denominator that's not 0, you're fine, right? You can never have a denominator of 0. So my run here is 1. So the way I set it up, I have a run of positive 1. I'm going to move to the right 1. All right, let's see what happens. All right, if I have to label this point. Sorry, this is 0, 4. And then, when I start from this point, again, from a point on the line, not the origin, from this point 0, 4, I start here, I go up or down 0 units. I don't move up or down. There is no rise. And then I move to the right 1. I'm at this location here. And there's the point, 1, 4. All right, I moved to the right 1 unit. So the x-coordinate went from 0 to being 1. And then let's do it again. Move to the right another unit, and then another unit, and then another unit, and then another unit. And I could have also said, hey, make this 0 divided by negative 1 and move left 1 unit, this point, and this point, and this point, left 1, left 1, left 1. All these points, 0, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4. This is negative 1, 4. Every single point on this line has a y coordinate of 4. That is what this is saying. This is y equals 4, f of x equals 4. No matter what I plug in for x, the output is 4. The y coordinate is 4. And so what we're seeing here is I have a horizontal line, right? Every single point on this graph has a y coordinate of 4, right? So it's parallel to the x-axis. All right. So there's the graph of this function called f. And what we're getting here is a horizontal line, right? When the slope of the line is 0, the graph is a horizontal line, like you're seeing here. It's straight left and right, parallel to the x-axis. Great. Okay, and I did the same thing I did with the other examples, right? If I recognize that I have an equation that can be written in this mx plus b form, f of x equals mx plus b, plot the y-intercept, plot a point on the graph, and then from that point use the slope, the rise, to go up and down, the run to go right or left, and find other points on the graph. And then once you have at least 2 points plotted, know it's a graph of a line, you can finish the graph of that line, fill the rest in. Wonderful. Alright, so as I like to say at the end of these, try your best, do the best you can to try to learn the material, understand the material on your own before you go asking for help. Read the material, of course. Read the author's examples. Perhaps even sometimes try to work out the solutions to an example before you see how the author did it, and then compare your work with the authors and see if you can't learn from mistakes there. Work on practice problems, work on exercises provided, try to find solutions if they're provided so you can check yourself and keep track of your progress. And don't just give up after the first attempt at a problem, the first approach. There are often many ways to do different problems in math, often many approaches that'll work. So try several ways to attack a problem. But if after several approaches at a problem, several attempts at exercises, you're still not getting it, still not working out, perhaps you should try reading the material again. Read it more slowly and deliberately. Take notes, because maybe after working on some problems, and reading through the material again, maybe you'll see something the second or third time through the material that you didn't see the first time, or perhaps you'll understand something will click better that the third time through reading it, the second time reading it, that didn't click the first time you read through it. But if after that, if after several read-throughs of the material and several approaches at problems, it's still not working out for you, you're still not getting it, well, then it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. So go ask a teacher, a tutor, a friend, someone in the class who you know knows the material well and is willing to help. Find supplemental materials online. There's plenty out there, easy to find. Find videos on the subject, maybe perhaps like this one, or plenty of videos out there that are better than mine. I assure you, they're out there and they're easy to find with a quick search. But just stay persistent. Don't give up. Keep practicing. And try to have a positive attitude as well. And I know that's easier said than done. A lot of people tend to go into math class thinking I've hated math my whole life and I'm not good at it and I never learned never could learn it well, and you just I hate it. But if you keep thinking that, you're going to keep hating it. That's not going to go away. Try to go into this with an open mind, thinking I'm going to enjoy learning this today. I'm going to sit down, I'm going to practice, I'm going to do things, I'm going to get it done, and I'm going to enjoy it. I'm going to have fun, I'm going to learn something and take something away from this, and have a positive attitude. And it's amazing the difference a little change in attitude can make in the learning process. So stay persistent, keep practicing, stay positive, don't give up, and I just know you're going to get it. I know you can. And thank you for watching.